Welcome to Chemistry in Detail. Today we are starting the unit Solutions. Most of the substances that we see around us are not pure in nature. They are mixtures. You've learned about the different types of mixtures last year. Homogeneous mixtures, heterogeneous mixtures. And solution is a type of homogeneous mixture. Now, what is a homogeneous mixture? A homogeneous mixture is a mixture whose composition is uniform throughout. A solution has two components. One is known as solute and the other is known as solvent. Solute and solvent makes up a solution. So without a solute and a solvent, there is no solution. And solute is the substance which is present in smaller quantity and is dissolved in the large excess of the other component. And solvent is the substance which is present in large excess and dissolves the solute in it. Example, sugar solution, salt solution, many other solutions are there. We'll take the simplest example. Let us take a salt solution. Suppose we take a spoon of salt and dissolve it in a glass of water. Salt is the solute and water is the solvent. Number of solutes in a solvent can be more than one. It is not necessary that only a single solute should be there. So there can be a number of components in a solution, but one is necessarily a solute and the other is necessarily a solvent. The nature of the solution will be same as the nature of the solvent. That is, if the solvent is a gas, then the state of the solution will be gaseous. If it is a solid, that is the solvent is a solid, then the solution will be a solid solution. We have a table here with the type of solution, solute, solvent and some common examples. For gaseous solution, the solvent will be gas. Solutes can be gas, liquid and solid. Example for gas and gas solution, mixture of oxygen and nitrogen gas. Liquid solute in gaseous solvent, example chloroform in nitrogen gas. Solid solute in solvent gas, example camphor in nitrogen gas. And for liquid solution, the solvent will be liquid. Gas and liquid, example oxygen dissolved in water. Liquid and liquid, ethanol dissolved in water. Solid and liquid, glucose dissolved in water. Now solid solution, the solvent will be solid. Gas and solid, example a solution of hydrogen and palladium, usually used in electrodes. Liquid and solid, amalgam of mercury with sodium, again used as electrodes. Solid and solid, example copper dissolved in gold. We are concerned with binary solutions in this unit. That means two components, a solute and a solvent. In this session, we are to discuss about the different ways to express the concentration of these binary solutions. Now, what do you mean by concentration? Concentration means the amount of solute that is dissolved in a particular amount of solvent. Qualitatively, you can say dilute solution, concentrated solution. You might have seen in the laboratory acid labeled as concentrated sulfuric acid, dilute sulfuric acid, concentrated alkali, dilute alkali. So dilute means a solution in which the solute concentration is less. And a concentrated solution refers to a solution in which the solute concentration is substantial. Understood? So this is the meaning of dilute and concentrated solution. We can say it qualitatively. You don't know the exact amount of solute present in the solvent. For various applications, we need to know the exact amount of solute present in a given amount of solvent, especially in the case of medicinal formulations. If the amount of solute is not exactly known, it's not accurate, then instead of healing the patient, it will lead to the death of the patient. So it is very important to maintain the concentration, to know the exact amount of solute present in a given amount of solvent. So there are various ways to express the concentration of solutions. We are going to learn them one by one. First method, mass percent or mass percentage. You have learned in your 11th standard about mass percentage. Mass percent last year. Mass percent can be defined as mass of one component. It can be either solute or solvent. Mass of one component divided by total mass of solution. Total mass of solution. Total mass of solution means mass of solute plus mass of solvent into 100. Let us take an example. 10 gram sugar dissolved in 90 gram water. You want to express the concentration of the solution in terms of mass percent of sugar. Mass percent is often represented as M by M, also W by W. So mass percent can be calculated in this manner. If you want to calculate the mass percent of sugar, then you have to take mass of sugar as component 1, that is 10 gram divided by total mass of the solution, that is 10 gram sugar plus 90 gram water into 100, that is 10 by 100 into 100, that is 10%. So 10% is the mass percent of this solution in terms of sugar. Next is volume percentage. Percentage or percent, both are same. V by V is the expression. It can be defined as volume of a component divided by total volume of solution into 100. Let's take an example. 10 ml ethanol in 90 ml of water. So we are going to find the volume percentage of water. Let's take the volume percentage of water. It can be any component, isn't it? So V by V of water can be calculated as volume of water, that is 90 ml divided by total volume of the solution, that is 10 plus 90. 10 plus 90 into 100 ml, isn't it? So 90 by 100 into 100, you get it as 90%. So the volume percentage of water in this solution is 90%. Another method is mass by volume percentage. This mass by volume percentage is used to represent the concentration of medicinal formulas. It is expressed as W by V. that is mass of solute in 100 ml of the solution. Another method is parts per million. Parts per million. It is expressed as ppm. If you want to express trace quantities of something dissolved in a solvent, you can use this parts per million. So usually the pollutants present in atmosphere, in water, trace quantities are expressed in this unit, that is parts per million. The calculation is number of parts of one component divided by total number of parts of all components. Hope it's clear. Number of parts of one component divided by total number of parts of all components into 10 raised to 6. This is the calculation. Number of parts of one component or any component divided by total number of parts of all components in the solution into 10 raised to 6. Suppose 1 liter of seawater. 1 liter of seawater means 1030 gram of water contains 6 into 10 raised to minus 3 gram of oxygen dissolved in it. So we have 6 into 10 raised to minus 3 gram of oxygen dissolved in 1030 gram of water. We are going to express this in terms of parts per million. For that, we have 6 into 10 raised to minus 3 gram of oxygen. So that is the number of parts. We are converting it into number of parts, this mass, and 1030 gram of water. Total parts of all the components in the solution into 10 raised to 6. You will get it as 5.82 ppm or parts per million. So you can convert anything, volume, mass, anything into parts per million. Next one, mole fraction. Mole fraction is familiar to you. How do you express the mole fraction? You express the mole fraction as chi. C-H-I. Chi. Suppose you have two components A and B. The mole fraction of A, chi A, can be represented as number of moles of A divided by total number of moles, that is number of moles of A plus number of moles of B. And chi B, that is the mole fraction of B, can be expressed as number of moles of B divided by Na plus Nb, that is total number of moles. Chi A plus chi B is equal to 1 or unity. That is the sum of the mole fractions of all the components in a solution is equal to unity. The number of components can be any number, and whatever be the number, the sum of the mole fractions of all the components will be equal to 1. Now we have a solved example here. calculate the mole fraction of ethylene glycol in a solution containing 20% of ethylene glycol by mass. We have to find the mole fraction of ethylene glycol. The information given to us is that 20% by mass of ethylene glycol is present in a solution. 20%. So you can assume that 20 gram of ethylene glycol is present in say 80 gram of water. So the total mass of solution is 100 gram, out of which 20 gram is ethylene glycol and 80 gram is that of water. To find the mole fraction of any substance, the formula is moles of that particular component divided by total number of moles of all the components, isn't it? So first we have to find out the number of moles of ethylene glycol. To find moles of ethylene glycol, you have to find molar mass, because mass by molar mass gives you the number of moles. So here the molar mass is calculated 12 into 2. 12 is the atomic mass of carbon, 12 into 2. 1 is the atomic mass of hydrogen, 1 into 6. There are 6 hydrogen atoms. Oxygen, 16 is the atomic mass of oxygen. 2 oxygen atoms are there, so 16 into 2. Total you got it as 62 gram. So moles 20 by 62, you got it as 0.322 moles. Moles of water, 80 is the mass of water, 80 by 18 gram, molar mass 4.444. So the mole fraction is 0.322 mole divided by total number of moles. It is about 0.068. To find the mole fraction of water, either you can take the number of moles of water divided by total number of moles, or you can simply subtract the mole fraction of ethylene glycol from 1, because it is a binary system. 0.932 is the mole fraction of water. Next is molality. It is again familiar to you, expressed as small m. Molality is defined as the number of moles of solute. Number of moles of solute divided by mass of solvent in kilogram. Number of moles of solute by mass of solvent in kilogram. So we have a question. Calculate molality of 2.5 gram of ethanoic acid and 75 gram of benzene. Molality, the formula to find the molality is number of moles of solute by mass of solvent in kilogram. So here you have to find the molar mass first for ethanoic acid, because it is the solute, and you have to find the number of moles of ethanoic acid. Mass by molar mass gives you the number of moles. So mass is 60 gram. You have calculated it here. 2.5 gram is the given mass divided by molar mass. You got it as 0.0417 mole. Mass of benzene in kilogram. Here it is given in gram, so you have to convert it into kilogram. Divided by 1000, you get it as 75 into 10 raised to minus 3 kilogram. So molality of ethanoic acid is 0.0417 divided by 75 into 1000. 1000 taken onto the numerator. You got it as 0.556 moles per kilogram. That is the molality of ethanoic acid. Next one, molarity. R-I-T-Y, expressed as capital M. Molarity is defined as number of moles of solute divided by volume of solution, not solvent, solution in liter. So, molarity is the number of moles of solute per liter of the solution. Molarity is affected by temperature changes. Why? Because volume changes with temperature. Question: calculate the molarity of a solution containing 5 gram of NaOH in 450 ml solution. So here we have to calculate the molarity of a solution. The mass of the solute is 5 gram and the volume of the solution is 450 ml. So molarity is defined as the number of moles of solute by volume of solution in liters. So first we can find the number of moles of NaOH, that is the solute. 5 gram by 40 gram. 40 gram is the molar mass of NaOH. All of you know that. You got it as 0.125 moles. Volume of solution in liters, 450 ml is given. You have to convert it into liters. 450 divided by 1000. You can convert it into liters. So here, substituting all those things into the formula to calculate molarity, you get the answer as 0.278 capital M, that is molar or molarity. Hope you understood all the different methods to express the concentration of solutions. So do many problems as you can so that you become proficient in it. We will meet in the next class. Thank you. Have a nice day.